type your name and what's your hold up. Sure. Here, I'll put something.
Do you agree?
Yeah. Here, you want to have the phone number? There. Joe, by the way.
Brian.
You want to get in the group me? The group me?
Yeah, we're gonna make a group.
Yeah.
There, give me my phone. Or he's got it.
I got your email. Okay, great. I'll look over some stuff.
Excellent. I hope it's at least a little helpful.
Yep.
Yeah, and we haven't really proved anything yet. But as we start to do more proofs, you'll get a sense of like what kind of proof skills will be required.
Sure. And do you want to add yourself also? Do you have group me?
Sorry?
Group me? Do you have group me? Yeah. Sorry. Alright.
Did all of them.
Sure. It's like a group.
Okay, so I guess we should start. At the end of Friday, we just started to discuss complex conjugation, right? And we made, again, as we will usually do, we gave an algebraic definition and then gave a geometric interpretation, right? It's just a reflection about the x-axis. I think we left on the note of the fact that the only complex numbers fixed by conjugation are the complex numbers with imaginary part 0, that is to say, real numbers. Just the x-axis is fixed by reflection about the x-axis. Okay, so that matches our geometric intuition. So I want to give you a laundry list of properties that conjugation possesses. Okay? So let's assume that we have two complex numbers, z1 and z2. Then we can make the following statements. The complex conjugate of a sum is equal to the sum of the complex conjugates. Complex conjugation behaves nicely with respect to multiplication of complex numbers as well. You can split conjugation across a product. This is perhaps somewhat redundant, but I think worth saying nonetheless. If we take the quotient of z1 and z2 and complex conjugate that, this is the same as taking the quotients of the complex conjugates. Okay, here's something that looks a little more interesting on the face of it, but once you start computing, it becomes fairly straightforward. The real part of z, I guess technically I should say z1 here, because I specified that z1 and z2 are complex numbers. So the real part of z1 is equal to the sum of z1 and z1 bar divided by 2. Okay? So once you remember the formula for complex conjugation, this becomes straightforward, right? The imaginary part of Z1 is negated in the conjugate, and then when we add them together, we get twice the real part, and the imaginary parts cancel, right? Because one is negated of the other. And then we just divide by 2 to just get back the real part. Okay? So analogously, we have a statement for the imaginary part of Z1. We take Z1 minus the conjugate of Z1. And what do I divide by here? Two I. Okay? Because, just think about this, when we flip the sign on the imaginary part of Z1, and then multiply through by a negative, right? That makes the real part of Z1 cancel with the negative of the real part of Z1 bar, right? Which is the same as Z1. And then we have the imaginary part of Z1 minus the negative of the imaginary part of Z1. So, and of course we still have the factor of I in here. So we cancel that I out. Remember, the imaginary part of Z1 is a real number. It's just the coefficient on I. Okay? Okay? If we consider the complex conjugate of the complex conjugate of Z1, we just get back to Z1. Yes?
Question on 4 and 5. I'm not sure if this is just like coincidence, but in DiffyQ we like talked about the complex representations of like sine and cosine.
Mm-hmm.
They kind of have like the real and imaginary aspects, like the Z1 plus Z2 over 2 and then over 2i.
Yeah, that's exactly analogous to this statement. In fact, later today we'll talk about the polar representation of complex numbers, and we'll recover exactly that which you're saying. Yeah, good observation. Yeah, we'll see that shortly. So this is sometimes in the literature or other places in mathematics, if you have a function that you operate twice on its input and get back the same thing, this is often called an involution. Okay, so we'll just say conjugation is involutive that's what 6 is saying. We're not going to necessarily use that terminology, but I like to throw in mathematical culture that you might encounter elsewhere whenever I can. So, property 7, the modulus of Z1 is equal to the modulus of Z1 bar. Okay? Think about this. Remember, the modulus is just the square root of the sum of the squares of A and B. Say Z1 is equal to A plus BI. So when we take the components of Z1 bar, we get, or when we take the modulus of Z1 bar, we get the square root of A squared plus negative B squared, which just becomes B squared, right? The negative cancels. Okay, and property 8, which will actually be kind of useful to us, is that Z1 times Z1 bar is equal to the modulus of Z1 squared. Okay, so this might seem familiar if you remember when you first learned about vector algebra. A similar formula holds for the dot product. That's no coincidence. The first thing we'll talk about after we finish talking about conjugation is the correspondence between two-dimensional vectors and complex numbers. Right? which we already kind of touched on in remarking that the complex plane is geometrically the same as R2, the Cartesian plane, right? We made this point on Friday that it's the multiplicative structure that gives us more in the complex plane than in the Cartesian plane. So you can kind of think of this like a dot product, and we'll make this precise very shortly. Okay? So, proof of two. Right? I kind of told you the proofs of some of these things in words just now. I think it's a valuable exercise for you to go back and write out the actual computations that you make to verify these statements. I'll show you two, but for homework, sometime before the next lecture, just convince yourself that all these things are true. Okay? And this is something I taught geometry over the summer. And a lot of people had not really taken a proof-based course in that class. So I really wanted to emphasize the point to them, and I think it's kind of important to emphasize this point to people who may not have had a lot of practice proving things. Very often, a computation can constitute a proof, right? Just doing some algebra to verify that something is true often constitutes a proof. So when I ask you for a proof of something, don't be intimidated. Just start, messing around. See what you can do with what you know. And then, after you get the basic idea down, then you can go back and kind of insert some words in between your computations to explain to the reader what you're doing and why you're doing it. Okay? But for all these, you can basically just straight up compute and show that these facts are true. Let's prove two together, just as an example. Okay. So let us write z equals z1 equals a1 plus I times b1, and z2 is equal to a2 plus I times b2. Okay, and then we'll just explicitly calculate both sides of this equation, right? So first, let's multiply z1 and z2 together, and then take the conjugate. Okay, so by our formula for multiplication of complex numbers, what does this give us? We get a1, a2 minus b1, b2 plus a1, b2 plus a2, b1 times I conjugate. Okay? And now I just flip the sign on the imaginary part. And that's just the definition of conjugate. Minus a1 b2 plus a2 b1 I. While on the right, so now I'll take the conjugates of each z1 and z2 first and then multiply them together. We have z1 bar times z2 bar, or in other words, a1 minus b1i times a2 minus b2i. Apply again our formula for multiplication of complex numbers. And what do we get? We get a1, a2 minus b1, b2 minus a1, b2 I minus a2, B1 I, or collecting terms, we get A1 A2 minus B1 B2 minus A1 B2 plus A2 B1 times I, right? I just factored out a -1 from both these terms and an I. And I wrote them this way just so it looks like the standard format we've been writing in. Okay? So you'll notice that these two agree. This is called a slug. It indicates the end of a proof. You'll see this in a lot of textbooks. I just do this out of idiosyncratic habit, in case you didn't know what the symbol is. Okay. So, right. So, I want you to notice something. Note, we already employed property 8. How? Where did we use the fact that Z1 times Z1 bar is equal to the magnitude of Z1 squared? And let me give you a hint. The important thing is that I've multiplied two complex numbers together to get a real number. That in general doesn't happen, right? When I multiply two complex numbers together, I'll get a complex number. But here I get a complex number which also happens to be a real number, right? Because the magnitude or the modulus of a complex number is a real number. It denotes the length of the complex number, right? Or the distance from the origin if we look at the point representation of the complex number. So where did we employ this? Does anybody have a feeling about that? Okay, I'll tell you. Yes?
It seemed like the A1, A2, B1, B2, the A1, A2 minus B1, B2. If B is equal to, or B1 is equal to negative B2, which is what the conjugate says, that term simplifies to A1, A1. So A1 squared plus B1 squared, which is the modulus of Z1 or of the complex number, and then the I term vanishes.
Yeah.
Because they cancel.
Yeah, exactly. So that's the proof that property 8 holds. Great. Fantastic. Let me point out where we used this already. Remember, we defined division of complex numbers by, if we have Z and W and C, W not equal to 0, Z divided by W, we want to put this in standard form. What do? We multiply by a fancy way of writing 1. W bar divided by W bar. Right? So this gives us a scalar, a real number, in the denominator. And that allows us to write the complex number in standard form. the complex number z divided by w in standard form. This is what we did, actually we did for first the numbers of the form a plus b times the square root of 2. Right? We rationalized the denominator, and then we defined the same thing for complex numbers. Right? Okay, good. So in fact, in general, this implies a formula for finding the inverse of a complex number, right? That is to say, 1 divided by z is just equal to z bar divided by the magnitude of z, or the modulus of z, squared. Right? I do the same rationalizing of the denominator here. That's, I mean, just insert the step that I skipped. Okay? Right? Just letting w equal 1. And I get z bar over modulus of z squared. Okay, this is perhaps kind of a handy formula to have. Okay. Right. So let us now talk about how. So on Friday we talked about the correspondence between complex numbers and a point in R2, right? The point representation of complex numbers. Now, you may remember from, for example, calculus 3, that points in the plane also correspond to vectors. Right? We just draw an arrow from the origin to a point in the plane, and that's the vector associated with that point. So, by transitivity, we can associate vectors to complex numbers. And we can associate complex numbers to points, and we can associate points to vectors. So therefore, we can associate complex numbers to vectors. Okay. So, let's discuss this in detail. Vectors and polar forms. Okay. So, recall. Vectors are objects which are characterized or determined by two quantities. What are those quantities? What characteristics determine a vector? Maybe like when you first study mechanics, I think, is often where people first start seeing vectors. And I feel like what's often said is that, yes?
Magnitude and direction.
Yeah, magnitude and direction. Before you start studying mechanics, for example, you're used to working with numbers, which are just quantities. When you start to study mechanics, you study vectors, which are quantities with direction, right? Or to said another way, magnitude and direction, right? So they're determined by two quantities. Magnitude and direction. Okay. So, in particular, what this means is that vectors are translation invariant. Okay? particular, vectors are translation invariant. What do I mean by this? Well, let me draw you a picture. Here's a vector in the complex plane. Yeah? Namely, we'll specify this by, let's say, I'm at, no, that's a little high. I'm at the point um, 1 plus I is how I specify this vector. Okay? What I mean by that vectors are translation invariant is that if I look at the vector which starts at the point 2 plus I and goes up to the point 3 plus 2I, these are the same vector, just translated. That's because the length, the modulus of these things is the same. And furthermore, this angle theta, if I were to draw a horizontal line, i.e. a line parallel to the x-axis or real axis, this angle theta is the same. Okay? So I can take a vector and move it anywhere in the plane. It's still the same vector. It's just translated. Okay? So, so what this means is we can characterize a vector by a single complex number by translating it so its initial point is the origin. Right? So that is to say, when I look at this vector translated here, I kind of am characterizing it by two complex numbers, right? But if I insist that I can translate any vector back to the origin so that it starts at the origin, then this other complex number that I'm using to characterize this vector becomes trivial, right? It's just a zero. So remember how we calculate this distance, the length of this vector. Or, how do we calculate this distance, the length of this vector, in terms of complex numbers? Remember, we derived a formula for the distance between 2 points in the complex plane.
Modulus, right?
Yeah, exactly. It's the modulus of the difference
Yeah.
of the points, right? So, this vector has a magnitude for example, the modulus of the difference of 3 plus 2i and 2 plus I, right? Which you can verify is the same as the modulus of 1 plus I minus 0 plus 0I. Right? That's the other complex number, the initial point of how I drew this vector first. Okay? So, verify that these are the same. It's really not that hard, right? We know how to subtract complex numbers. We get the same complex number. Okay. Good. So, this will be our convention. When we will specify a vector by a complex number, we assume that that means its initial point is at the origin. Okay. Therefore, a vector characterized as a complex number Z has length the modulus of Z. Okay? And that is to say, once we translate back to the origin, we're just looking at the size of this complex number. Right? When we want to determine the magnitude or length characteristic of the vector. Okay? So, let us remind ourselves how to add vectors together. And, okay, so we're building this correspondence. Let me give you a broad view of what we're actually doing. We're building this correspondence between complex numbers and vectors. And what we would like is to have as much of the same structure between those two things as possible. Right? That is to say, vectors are objects that can be added together. And so are complex numbers. Right? We defined that algebraically on Friday. What we have to check to be rigorous, to commit real mathematics, is that the notion of addition of complex numbers agrees with the notion of addition of vectors. And that under this correspondence that we're describing, those notions exactly match. Okay? So let's remind ourselves first of how vectors add. And then check that that agrees with what we defined addition of complex numbers to be. Okay? So, let's let V1 hat and V2 hat be vectors in the complex plane. Determined by complex numbers Z1 and Z2 respectively. Then we add V1 and V2 by the parallelogram law. Okay, I'm actually gonna not try to squeeze this drawing into the rest of that board. Give myself some space here. Okay, so I have some vectors. Let's call this V1, okay, and as our representation goes, it's characterized by the complex number Z1. And let's say we have some other vector. Let me put this over here. V2, characterized by the complex number Z2. So, what is the parallelogram law? Remember that vectors are translation invariant. So, as long as my two vectors are not parallel, I can form a parallelogram out of them. Just by sliding V2 along V1, V2 translated, and then likewise translating V1 along V2. Okay, so I form a parallelogram in this way, and then I draw a diagonal, which I'll call just V. And I'll say what that is over here. V is defined to be the sum of V1 and V2. Okay, this is what the parallelogram law means. I form a parallelogram and draw the diagonal, and that is defined to be the sum of the vectors V1 and V2. Okay? So, I want you to notice this picture. Implies the commutativity of vector addition. Right? That is to say, another way of thinking about this is I haven't drawn a parallelogram, I've drawn two triangles. Right? I've drawn a triangle with sides V1, V2, and V, and a triangle with sides V2, V1, and V. That is to say, it doesn't matter what order I traverse V1 then V2, or V2 then V1. Okay, again, second, right? A computation constitutes a proof, very often. What I just said constitutes a proof of this equality, that addition is commutative for vectors. Okay? Just to give you some idea of how broad the notion of what a proof can be is. Okay? Okay, good. Let's say, let's go back to what we were trying to do, verify that addition of complex numbers agrees with addition of vectors. So, if v1 is equal to x1 plus I times y1, and v2 is equal to x2 plus I times y2, well, okay, in the point representation of the complex plane, or of complex numbers, that means in the plane, this is the point x1, comma y1, and this is the point x2, comma y2, right? So now when we represent the vectors v1 and v2 hat as points in the plane, we get just that the vectors v1, well, let's just say v1, the vector v1 hat is equal to the point x1 comma y1, and v2 hat is equal to x2 comma y2. Okay? So all I'm doing is resolving both complex numbers and vectors into a representation that uses points in the plane. And the only difference here being this I component in the complex numbers. It doesn't appear here with the vectors. Okay? So we know how vectors add algebraically, right? They just add component-wise. And you can see that geometrically as well, right? I go, that is to say, let me write this down, x1 plus x2, comma, y1 plus y2. Okay, so let's say we traverse v1 first, then v2. So for the first component, we go out the x amount for v1, and then out the x amount for v2 from where we ended up with v1. That means this point here is x1 plus x2. Same for the vertical component, right? First I go up the amount to get to v1, and then up however much I went to get to v2. So that's how I get y1 plus y2. Okay? So, of course, this is just equivalent to the algebraic definition we gave for the sum of complex numbers. So our notions of addition agree. Great. I know it might seem like I'm making a big fuss about nothing, really, but I already showed you, or I hope I convinced you on Friday, that the multiplicative structure of the complex numbers is not present in points in the plane. And if you remember, when you learned about vectors, there's no good way to talk about how to multiply vectors together in general. That gives you back a vector. You can take the dot product of vectors, but that gives you a real number. And you can take the cross product of vectors, but that's only in R3. Right? So, given that there is additional structure to the complex numbers that vectors don't have, it's somewhat important that we verify that addition agrees between vectors and complex numbers. And so, that's what we've done. Okay. So now that we have this correspondence, we'll often just say the vector z, meaning the vector that's specified by the complex number z. Okay? So, in light of this correspondence, recall that the length of any side of a triangle is less than or equal to the sum of the lengths of the other two sides. So, because we carefully established this correspondence, this fact from geometry gives us an inequality for multiplication of complex numbers. Okay? Let me make this precise. This is historically called the triangle inequality. We take Z1 and Z2 complex numbers, then the modulus of Z1 plus Z2 Z2 is less than or equal to the modulus of Z1 plus the modulus of Z2. Right? That is to say, the modulus of Z1 is the length of V1 in our diagram here. And the modulus of Z2 is the length of V2. Right? And the modulus of the sum of V1 and V2 is the modulus of Z1 plus Z2. So this leg of this triangle, this leg V has modulus Z1 plus Z2, and it must be less than the sum of the lengths of the other two legs of this triangle. Okay. So, just from the algebraic definition of complex numbers, this isn't at all apparent. You have to do some work to prove this. But once you make this correspondence precise, you just look at this picture, and it has to be true because of triangles. Okay? So, here's a consequence of this theorem. Notice that the complex number Z2 minus Z1 plus Z1 is equal to Z2. That's a trivial statement, right? But what does that tell us? Well, let's apply our theorem to this situation. So, this implies by the triangle inequality that the modulus of Z2 is less than or equal to the modulus of Z2 minus Z1 plus the modulus of Z1. Right? I have two complex numbers that add together to this. So that's just plugging into what the theorem says. Now, another way of writing this is that the modulus of Z1, modulus of Z2 minus the modulus of Z1 is less than or equal to the modulus of the difference of Z1 and Z2. Okay? So, kind of an analogous statement for subtraction of complex numbers, which we derive by this seemingly trivial statement, right? Some kind of formal trick. Okay, so this also points to a geometric interpretation of the difference of vectors. Okay, so remember again, the modulus of z2 minus z1 is the distance between the points representing z1 and z2. So that is to say, I have some point representation of z1, and I write the vector representation at the same time, z2. So the magnitude of this vector, z2 minus z1, is the distance between these two endpoints, right? So the complex number z2 minus z1 represents this vector that points from the endpoint of z2 to the endpoint of z1. Okay? It's when we add vectors, we use the parallelogram law. When we subtract vectors, we just leave them initial point to initial point. Right? The parallelogram law tells me that to add vectors together, I have to go from the initial point of one to the endpoint of the first one, and then put the initial point of the second one at the endpoint of the first one, and then go to the endpoint of the second one. And then I go from the first initial point to the last terminal point. That's how I add. To subtract, I just leave them end to end. Okay? I might ask you to make some explanation of that in the homework, because it's good practice for the geometric intuition of what's going on here. And I'll give you a hint now. What happens when you multiply a scalar vector by -1?
You flip its direction.
You flip the direction. Yeah, you put the head of the arrow on the other end. Okay? So think about that. I think I'll include something about that in the homework. Okay, good. So, what else can we say? The point of making the correspondence between vectors and complex numbers precise is that now all the facts we know about vectors can be applied to this new object which we're developing, the complex numbers, right? And we've, in some certain sense, enriched the geometry of the complex numbers by making this correspondence with vectors. Okay? So here's a theorem. three complex numbers. Z1, Z2, and Z3 lie on the same line in the complex plane. If and only if the difference of Z3 and Z2 is equal to C times the difference of Z2 and Z1 for some real number C. Okay, so can anyone remind me how to tell when two vectors are parallel?
Yes. The dot product is twice the magnitude. Or no, the square of the magnitude.
So the dot product, that's almost right. You might have some scalar squared in there, right? And that's because the correct formulation is that two vectors are parallel exactly when one is a scalar multiple of the other. So you might have a scalar squared, because you'll have the vector dotted with itself times some scalar, right? Or, yeah, it's not squared, it's just a scalar would come out. And then you get the magnitude of whichever one you wanted squared. Okay, so here's a sketch of a proof, right? Two vectors are parallel exactly when one is a scalar multiple of the other. Okay? So, if we take this equation, right, this says that the difference of Z3 and Z2 and the difference of Z2 and Z1 are scalar multiples of one another, right? So, this is exactly what Z3 minus Z2 equal to C times Z2 minus Z1 means. Says Z3 minus Z2 is a scalar multiple of Z2 minus Z1. Okay? So what that means is that if I translate both these vectors back to the origin, I'll have a picture as follows. Let's see. I'll have Z1, Z2, and I'll have Z3 here. Okay. And of course here I have v2 minus v1, and this whole distance is, oh, sorry, that's not what I meant to say. This distance is v3 minus v2. So they have to be on the same line, right? These two vectors have to be parallel. That is to say, when you put them at the origin, or end to end, they are in a line together. Okay? That's the sketch of the proof. This is, so I'll leave it empty because I didn't say exactly everything. Okay. Okay. So let me say what we've done in yet another way. We've demonstrated that vectors and their additive structure are characterized by the parameters the real part of Z and the imaginary part of Z. Right? This is kind of a trivial restatement of what we've done. Right? That is to say, vectors are characterized by two real numbers. Right? We're forgetting just the I in Z, and that characterizes vectors. Okay, but we might want to go back and think again of our intuitive description of vectors, that they are characterized by the parameters of magnitude and direction. Okay, and the question is, can we extract those data from a complex number Z? Well, we already did one of those things. We extracted from Z the length of the vector, right? That's just the modulus. Extracting the direction from Z is actually surprisingly complicated. We're going to spend a little time talking about that. Okay, so how do we extract the naive parameters characterizing vectors, by which I mean magnitude and direction? Well, let's make yet another picture. So here's some complex number, Z equal to X plus I, Y. Okay, so I have Y here, X here, and we have what we'll call R equal to the modulus of Z, which is equal to the square root of X angle theta. Okay, so we know the length of a vector in terms of x and y. Of course. So I haven't said this explicitly, but this is exactly what we mean by direction. It's once you translate a vector back to its, so if you make it its initial point at the origin, the counterclockwise angle from the x-axis is what we mean by direction. Theta is what we mean by direction. Counterclockwise angle from the x-axis. So, given the two parameters that we have convinced ourselves characterize vectors, how can we compute the angle theta using these two parameters, the real part of z and the imaginary part of z, or x and y, as we have it written on the board here? Yes?
Inverse tangent.
Inverse tangent, yeah, great. I should mention, we'll always use radians in this course, which we measure in radians. Okay. Let me just also add the parameters r and theta are called polar coordinates. So, right. Let's do something slightly easier to warm up to get to talk about how we compute theta. So, taking the inverse tangent is definitely intuitively the right idea, but there are some complications that arise. Okay, so before we do that, it would be ideal, okay, so we know how to compute r based on x and y, and I'm postponing the discussion for how exactly we compute theta from x and y. Let's go in the reverse direction first. Given r and theta that specify some vector, how do I compute x and y? Yes?
Sine and cosine.
Yeah, we'll use trigonometry. Yeah, that's exactly right. So let's just say to obtain x and y from r and theta, use the following formula. X is equal to r times cosine of theta, and y is equal to r times sine of theta. Right, that's just regular old trigonometry here on this right triangle. Okay, so now let's discuss theta. Okay, Trigonometry also tells us that theta is equal to the inverse tangent of y divided by x. However, what is the range of inverse tangent? Goes back to calculus 1.
Negative 2 pi, or negative pi over 2 to pi over 2.
Yeah, exactly. Good. Open or close parentheses in that interval. Open. Yeah, right. Because you can't put a 0 in the denominator, right? And that's what you would do if you were to take the inverse tangent of pi over 2 or negative pi over 2. Okay, good. So, however, inverse tangent has range negative pi over 2 to pi over 2. So it's not enough. What do we do when we have some vector over here with angle theta prime? How do we compute this? Well, any suggestions on that?
We could add cases based on the sign of x and y.
Yeah, that's a great suggestion. We could just add what would we add here? A factor of pi. Add or subtract a pi whenever appropriate, right? Depending if we're in the second quadrant or the third quadrant, right? Okay. So, and in fact, that's what we'll actually do in practice. But let's be more precise. So I'll write this down. To correct this, we may add or subtract pi to the output of inverse tangent of y over x. Depending on the signs of x and y, right? That is to say, if x is negative and y is positive, we would add or subtract. Add a factor of pi. And if both x and y are negative, then we would subtract a factor of pi. Right? I think I'll make this homework exercise as well, writing down a formula for this precisely, just to give you a preview. By the way, I guess I'll mention this now, just because I happen to say it. Later today, sometime this evening, I'll post a homework assignment to Canvas, which will be due the following Tuesday, next week. Okay, I have a full week to work on it. Okay, so, right. This is what we'll do in practice. This is what we'll do in practice. But another thing we could do, we can uniquely determine theta by insisting it satisfy both theta is equal to inverse cosine of x divided by the magnitude of z, and theta must also be equal to the inverse sine of y divided by the modulus of z. Okay, this is another more technically correct, less ad hoc way of uniquely determining theta. Okay. So let's give. So doing this corrects for the the range restriction of inverse tangent. Unfortunately, we still haven't. What do I mean by uniquely determined? What do I mean when I say uniquely? In fact, in general, in mathematics, whenever you say something is unique, you have to say what precisely you mean by that. And what I mean by that here is that theta is unique up to adding a multiple of 2 pi. Right? That is to say, if I sweep out some angle theta that is the complex number that has that theta can also be represented by that theta plus 2 pi. I can rotate yet again around the plane. In fact, I can rotate as many times as I want around the plane. So, uniquely determine theta by insisting it satisfy these two equations up to adding a multiple of 2 pi. Okay, so we do better with this, but still not good enough. Okay, here's the definition. An argument or phase of a complex number z x plus iy is an angle satisfying both of our equations. Well, I wrote magnitude with you before. Why don't I stick with that? Okay, which we denote R of z. Yes?
Well, so the range of cosine inverse is 0 to pi, right? And the range of sine inverse is minus pi over 2 to pi over 2. But, so what do we do if theta is in the third quadrant?
The third quadrant, okay, so, so let's see. that will give us a negative y and a negative x, right? So what is the range of inverse sine again? It's
Same as tangent.
yeah, I guess so. Huh. So let's see. Huh. I don't have a good answer for you off the top of my head. I'm sorry. So we'll have to come back to this. As soon as I clear this up, I'll write something up and send you all this after class. Or think about it for yourselves. But I will send you something that gives some explanation of this. Yeah. Sorry, I don't have an answer for you right now. Okay. So.
Well, maybe it's just a matter of taking the inverse function of a vector as opposed to a scalar.
But our inputs are scalars here, of course, right?
Yeah. But there's no way to just kind of like, if you give someone a scalar, there's no way to determine theta. I feel like the input should be the whole vector as opposed to. Does that make sense?
How are we doing on time? Okay, we have 18 minutes left. So I'll ask us to just hold off on this point. I might be saying something wrong here. I might have screwed up the definition of how to define theta somehow. And I'm kind of on the spot now for how to explain myself. So let's just come back to this point, okay? I'll clear this up as soon as I can and send you all a message as soon as I can say something coherent. Okay, I just feel like I could stand here for the next 18 minutes and not come up with anything worthwhile to say on this point. But thank you for bringing this up. This is a good point. Okay. So, for the time being, let's just note that once we have a correct definition for how to determine theta, notice that I say an argument here. This is to reflect the fact that we can rotate as many full rotations as we want once we determine some value of theta, which characterizes our vector. Okay? So, right, that is to say, if theta naught is such an angle, then the set of all such angles is given by theta naught plus 2k times pi, where k is any integer. Okay. So what we'd like to do is come up with a related function that gives us a specific argument. It chooses some element of this set. Right? This thing I defined, arg of z, is not a function, right? Because it assumes many values. There are infinitely many values that are output by arg of z, so this is not a function. Our goal is to construct a function which chooses some value out of this set. Okay. Okay, so right. To make the notion of argument less ambiguous and more computationally useful, we can make a choice of half open interval for the output of arg of z, that has length 2 pi. Right? That is to say, I want to choose just something around some value theta naught, some range around theta naught that just contains one angle for each possibility of a complex number lying on that angle, or being characterized by that angle. Okay? Right. So, here's some definitions. So, choice of such an interval is known as a branch. Okay, so there's some geometric motivation behind this terminology, which I'll draw a picture of after we say this set of definitions. Okay, so secondly, the branch that produces a value for the argument in the interval open bracket negative pi to pi close bracket is said to be the principal branch. Or actually, sorry, the principal value. Principal value of the argument, which we denote capital R of Z. Okay? This is a function. Okay? So any choice of branch turns lowercase r of Z into a function, right? It restricts it to have a single value for each input Z. Okay? That's why we choose a interval of length 2 pi. So there's exactly one value for each Z, instead of as many values for Z as there are integers. Okay. Okay, and why do we call this the principal value, this particular choice of branch? Well, if you look at it, it is a schematic diagram. Here's my open parenthesis at negative pi. And here's my closed parenthesis at pi. So this kind of somehow matches how we usually think of angles in trigonometry. That is to say, we place some special importance on the x-axis. And I could choose anywhere to cut this, to make this discontinuity, but we call this the principal one because it reflects our intuition most. Okay? Okay. So, notice the function capital R Z is discontinuous at all values I should say all input on the negative x-axis. Right? The limit approaching from both sides of the argument for any value along the x-axis, the negative x-axis, we have a gap here, right? We have two different values as we take the limit from both sides. Okay? This half line of discontinuities is called a branch cut. Okay, so let me just motivate why we call these branches and what we mean when we say branch cut. This has a kind of geometric and topological meaning. At first, when we start trying to pin down how to compute the argument of some complex number, it seems like perhaps this is just some annoying inconvenience, this ambiguity that we run into when we try to characterize these angles, theta. But in fact, there's a deep geometric meaning here. The geometric slash topological meaning of the definitions of argz and capital RZ is that the complex numbers when parameterized by the modulus of z and lowercase r of z form a spiral sheet, or if you like pasta, a piece of rotini. This squiggle shaped pasta, right? So I'm not much of an artist, but let's see what I can do here. So we have come like this and like this, right? So maybe I can tighten this up a little bit. There really isn't much of a hole here, but so for each revolution of 2 pi, I have another copy of the complex numbers, right? So, or that is to say, each of these sheets are branches, right? Each of these turns is what we define to be a branch. So then, when we make a branch cut, what we're doing is just cutting at a certain place so that we just look at a single branch. Okay? So, that is to say, let's make this line, this should be a dotted line, sorry. And then, let's say the next one up is the solid one, right? This kind of corresponds to open and closed here. So, branch cuts. Well, actually, this is just a branch cut, right? I have to cut in two places to get exactly one. Okay? Right, so let me just say that this interpretation of what's going on is kind of the starting point for studying complex differential geometry, or the study of complex manifolds, is that the complex numbers themselves form this multi-sheeted thing. Okay, so if you pursue complex analysis much further, then this will be the starting point of how you ascribe topological and geometric meaning to what's going on. Okay, so that takes us to time. Really sorry for fumbling this whole definition of theta. I'll be sure to remedy that as soon as we part ways here. Also look for the homework assignment tonight, and